So I'll go over briefly about load balancing in general. So let's say, in a dynamic scenario, we know load balancing is quite useful and all that. Let's look at a static scenario where the domain load doesn't change over time. But if it's an irregular application, when the user decomposes the domain, it could so happen that certain domains have a larger load compared to other ones. So what do? The programmer will have to explicitly say how to map these domains onto the processors. But we don't want to burden the programmers with taking care of mapping the domains depending on the data set or the size at which you're running, etc., etc. So that's a static case. The other case is dynamic case, where many applications are becoming more adaptive in the sense that they're using algorithms which do adaptive refinement. So all of a sudden you may have a large increase in the load. You spawned many more tasks, and then there could be a load imbalance due to that. So, and such an example is AMR, adaptive mesh refinement. The other case is when there is a gradual change of load. Let's say in molecular dynamics simulation, the atoms move from one region to another region, or in cosmology, the particles move from one char or object to another char. So this also introduces load imbalance during runtime. So that is the dynamic case. So the best way to and what is wrong with load imbalance? So the thing is, the scalability or performance is limited by the most overloaded processor. It doesn't matter who are very less loaded or things like that, or very close to average load. But if some processor is 10 times more than the average load, then that is going to determine what is the time step or what is the performance of the application. That's why we want to make sure that the load is balanced among the processors, so we don't have scalability problems in future. And as we as we go to larger and larger scales, the chance that just one processor is going to become much more overloaded than others is going to increase. So that's why it becomes even more critical to improve the load imbalance problem when we go to larger scale. And we are essentially wasting resources, right? Like if some of the processors are just sitting idle doing nothing, then it's a wastage of resources also. So in Char, the over decomposition along with migratability empowers the runtime system to do all these tasks of load balancing. So the runtime system is going to monitor the application, and whenever it notices that there is a significant load imbalance there, then it identifies that there is a load imbalance, so it can trigger the load balancing process. And the load balancer will get all the load statistics, which is being collected automatically by the runtime system, and do the necessary load balancing that is required. Because we have over decomposition, it can migrate some of the tasks from the overloaded processor to the underloaded one. So that's the essential idea of load balancing. It's supposed to be a video, GIF basically, but here it's a Brazilian weather code simulation. This was the work done by Eduardo and Celso Mendes with a collaboration with Brazilian University. So here what we are seeing is this is the domain that we are looking at, and this is the storm that's coming in. It's a nice animation, in fact. We could have watched it. So if we just decompose this normally, let's say among 4 processors, then the region or the domain that's containing the storm has the most work. That's the most overloaded processor. And as the storm moves from, and the storm is not stuck at one place, right? It moves from one domain to another domain. And as it is moving from one region to another region, another domain is going to get overloaded. So this is a very dynamic application which requires frequent monitoring and frequent load balancing to ensure good performance. So this is 64 processors on a grid, and color coding shows how much of a load is there on each processor. Red means there's a high load there, and blue means there's very less load there. So wherever the storm is moving, those processes are going to get much more overloaded than the others. So let's look at first over decomposition in this case. The left case is when you have 4 processes and the domain is exactly divided into 4. That's the usual case in MPI. So here, there is no scope of any load balancing or, balancing the load. So wherever the storm is set, whichever domain the storm is set, that process is going to be much more overloaded. In over decomposition, we'll further divide this domain into many more work and data units than the execution unit. So here, let's say you have only 4 processors. We can further divide this 4 domains into another 4, and total 16 over decomposed domains mapped onto 4 processors. So each will, if they're evenly loaded, they'll probably get 4 domains per core. So this is a study that was done. So the idea of moving from actually the weather code was written in MPI, and they had run into many problems with load balancing. They wanted to experiment with Charm. So they ported their MPI code into Charm using the AMPI framework. If the code is very well written, like Lulesh 2.0 was very well written, so we could easily import it into Charm just with very basic flag changes or things like that. And we could get all the benefits that Charm offers, like over decomposition, load balancing, etc., etc. So this is the original MPI code, where we can see that the minimum utilization is just about 30% and maximum is only 55%. This is 1 process per core. There's just one object per core. This is pretty bad utilization, and this only. So here with over decomposition, now what happens is that if you have over decomposed objects, at least when one object is waiting for communication to happen, the other object can overlap that part and then improve the performance overall. So that's what we see here. So at least the average utilization increased a bit, and the minimum went from 30% to about 55%. And the maximum is. Still, we can see that the utilization is not that good because there is still load imbalance, because of which when one process is busy doing work, there are other ones which are idle. So over decomposition helps a little, but with load balancing, what they found is it can give very good utilization with almost 85 to 90% utilization. So this is a very good example to show that the load balancing helps. The other problem that they had run into in this particular code was, the load balancer is not a free thing. You have some overhead associated with it. So it has to take care of migration, it has to take care of doing the strategy, etc., etc. So how often do we want to do the load balancer? That's also another critical thing, because if you do it very frequently, then the overhead of the load balancer will be more than the benefit that you get. So in this application, they kind of hand-tune it and try to figure out what's a good period to do load balancing. But after this, we have now a framework called Meta Balancer, where you can the runtime system or the Meta Balancer framework will watch the application, collecting very minimal stats like what is the average utilization, what is the max utilization. And then it also has information about how much overhead the load balancer is going to take. So depending on what is the benefit you're getting and what is the overhead that you're going to incur if you do load balancing, it will decide, okay, it is best to probably do it at X frequency and not more than that. So, and that's another addition to this thing. So finally, we see that over decomposition with message-driven execution. I also gave the talk yesterday about these things, but basically they help in many aspects. That is, you can, because there is over decomposition, when one work unit is waiting for some message to arrive, the other work unit can start doing the work if it's already ready, and thereby we can eliminate or hide the latency that the messages occur. And so we can overlap communication with computation. With migratability, many other features get enabled, like we can do load balancing, fault tolerance. So the runtime system will migrate the chars from one, and the process that has that is dead. It has already checkpointed some of its data into the buddy process. When we have to restart, we'll move all those information to a new process. That's because we can migrate these chars. And there's job, malleability, and many things that we can do with migratability enabled. And then finally is the over decomposition with migratability and asynchronous message-driven enables an introspective runtime system. So many features like temperature, constraint, all this we can do with an introspective runtime system, because it can watch and because it can migrate chars, it can do many other things like that. So this is all I'll talk about. In case you have more questions about specific features, I can go into detail.
Okay, so now we're going to have a little bit more in-depth into the tutorial. So we got you started with a very, very simple, let's run a main that creates one char and prints out some stuff. So now we're going to go into a little bit more detail on both the file structure and some of the coding features that Char++ has that you can take advantage of, and also touch a little bit on what common practice is when you're writing programs in Char++. So again, we've already kind of talked about this. Anyone familiar with C++ objects, you're going to define those in your .h and .c files just as you normally would with a few extensions. The main extension being now we will also basically specify which of these objects are our char objects and which of the methods of those objects are our entry methods, which can be invoked remotely using a CI file. So again, the CI file just says, it gives an interface to Char saying, here's our chars, here are the messages you can send them via remote method invocation, and again, those methods will also be defined in the .c file. So more details on the interface file, which we very briefly touched on before. Charm programs are organized just as a collection of modules. Each module has one or more chars, so you can define whatever chars you need in each particular module. And then the module that does contain the main char is declared the main module. And whenever you compile a module, you end up with this pair of header files, this decal.h and this def.h. And those just need to be included in certain ways in your actual C++ header and C files. And that's what contains all the auto-generated code that allows you to do things like remote method invocation and addressing chars via proxies. So again, chars are our parallel objects. These are the actual entities that are managed by the runtime system. We give them a set of entry methods in the CI file. They can be invoked remotely as long as any other char knows the address of some other char in the system. It can remotely invoke a method on it, as long as it's one of these entry methods. So right here, the following code, we have a char in the CI file. It's just a char called MainChar with some method definitions. When we compile it with charm C, it'll just generate a C++ class cbase underscore MainChar. So you're always going to end up with classes cbase underscore and then whatever name you give the char in the CI file. And then the generated class is extended and implemented in the C file. So again, here you'll have the name of your char again, class MainChar, and it inherits from this generated base class. So our entry methods, again, they can be remotely invoked, and that invocation is asynchronous. So in the CI file, you'll have, for example, your constructor. Then you'll have, here we have two declared entry methods. One entry method is foo, takes no parameters. Your entry methods can also take any standard parameters. For example, this one takes an int as a parameter. And then in the C file, just like for any other method, you would define them MainChar : whatever the method is. You have your constructor code for the foo, and code for bar. We touched on this a little bit before, but the MainChar constructor is where the execution begins in the Char++ program. So it takes a ck-arg message, which just contains the usual parameters you expect in main, argc and argv. And this is where you will normally set up your system. So you enter in the main chars constructor, and that's where you'll usually set up what other chars are going to be in the system, setting up, passing them proxies so they know how to communicate with each other, etc. So for actually creating a char, if we have this in our CI file, to instantiate it, we call the cknew method, the static method on the proxy. So we have a proxy for the char we're trying to call. That this is the generated class as well. And then we call cknew, and we pass it the constructor arguments. So whatever arguments you've defined in the entry method for the constructor in the CI file, that's where you would pass them here. And then to communicate with the class in the future again, instead of just creating this new class, we also want to store its proxy in some variable. So we've declared a variable to store the proxy. We create the char and store it later, and then we can actually do the remote method invocation, which we'll talk about here. A little more about proxies. Just like in C++, if you want a pointer to the object itself, you have this. In Char++, we also have a proxy to ourselves. So this proxy is included in the base class of each char, so it can refer to itself. And this way it can inform other chars about itself. So a char can send along its proxy to other chars, so then other chars can, in the future, communicate with it. So again, proxies can be passed to methods. And in this snippet here, we have a entry method that foobar2 that takes in a proxy here to a main char called main. And then in the C file here we have the definition of this entry method. We have pass in our main, and then to invoke a method on a proxy, we just do main dot and then whatever method we want to invoke. So in this case, here this line of code would actually invoke the foo method on main remotely, so the runtime system would handle that, looking up where main actually resides in the system, packing up the message, sending it to main, and then with the message-driven execution, once the message arrives, this foo will be called by the scheduler on the main object.
But you don't do main : which you did for cknew.
Right, cknew was just
special.
So if we go back, yeah, cknew is just a static method defined on the proxy class, so you don't need an actual instance. Just like in C++, when you have static class level methods, you just call them on the class, but then when you have things you actually want to invoke on specific objects, you call them on the specific objects. Same here, so there's nothing stopping you from creating multiple chars that are of type main. So this just says I want to send this foo message to this particular proxy, which refers to some specific char in the system. And for charm termination, again, we saw ckexit before. It ends the parallel execution on all processors. You only have to call it on one, and that performs all the cleanup for charm itself. So instead of calling exit, like in the traditional sense, which would only terminate one process, we just want to make sure that when you're exiting a charm program, you call ckexit, which handles all the cleanup the charm needs and ends the entire application on all processors. And again, this can be called from any char on any process. It doesn't need to be called from main or from a particular PE in the system. It can be called from anywhere. Okay, so here is the example that we touched on briefly before. We can go over this in a little more detail. So again, we have some module. In this case, it's called my module. I think in the example code I renamed it so it doesn't collide with all the other examples. So we have two char declarations. Each one is very simple. They only have constructors, no other entry methods. Again, simple takes in two parameters in this constructor. So then when we look in the actual C file, we define the two classes for each char. Main, again, inheriting from the generated base class, as well as simple, inheriting from its own generated base class. And then in main, we have our entry to the execution of the Charm++ program. It prints out a message, reads in some arguments, and then it goes ahead and uses cknew to create a new simple char. And notice here we pass in the arguments we want to be passed to the simple char constructor, so that when that char is actually executed, you will see a hello message telling you what PE it's run on, and then a message involving the parameters.
One question on that. The header files at the top and the bottom, do they have to be in the quote form, or could you use the arrow?
I think they would have to be in the quote form because they're going to be in the local directory. Yeah.
Unless you specify your local directory as a path in the build or something.
Yeah,
Right.
Yeah, exactly. If it's in the same path, it can be echoed back.
So again, if we run this char create example like we just looked at, we see from the main char we have our hello world message, and then from the simple char we have two messages, one saying where it's running from, and one saying something about the radius of a circle. If we run it again and pass in an argument, since the main char takes an argument, now main prints out an additional message saying hello PPL or whatever argument you pass in. Okay, so for asynchronous methods, entry methods look like any other C++ method call. It's now, instead of calling them on an actual object, we're calling it on the proxy. So here we have a brief example of creating a new proxy for some char MainChar with whatever arguments we might need to pass it. We store the proxy in a variable, and then if we want to invoke methods foo or bar on the proxy, we just do it as if it were any other method call on an object. So again, the runtime system is going to see these, pack them up as messages, find out wherever this the char referred to by this proxy is actually located, send those messages over the network, and then once those messages are picked by the scheduler on the char's PE, the methods will be executed. And again, just to iterate what we mentioned before, we also always only guarantee for each PE there's exactly one char executing at a time, and that char is only executing one method at a time. So even though we're calling two methods on this proxy, we know that foo will run as one contiguous method on the proxy, and then bar will run, or vice versa. Bar may run first, and foo will run, but we know there won't be interference between the two methods. They won't be running at the same time, so we don't need to worry about them with data races on the fields of that char or anything like that, because we have this non-preemptive execution. One of the tricky things with asynchrony, especially when you're used to something in a more synchronous parallel system, method invocation is not ordered. So in this case, calling foo and then bar, there is no guarantee that foo will execute before bar. So when the messages arrive, they're executed. So bar, if the bar message arrives first, we'll see bar executes this message and then the foo message, or we may see the foo message first and then the bar message. So that's something you have to be aware about. And again, just to keep things general, the Charm++ runtime doesn't enforce any ordering on message arrival or message sending. However, we give you constructs for doing that on a per char level. So the chars that do need specific causality and control flow constructs, you can do that on the per char level. This also goes for invoking the same message twice. So if we call bar with 7 and then 5, we might see them print out in either order.
So can you grab those messages before they invoke their char? Is there a higher level, or do you have to have?
So for as far as ordering goes, we're going to look at something later in the tutorial called Stag, and that will allow you to not explicitly grab them per se, but enforce an ordering them on them. Yeah, we'll get to that later in the tutorial. So here's just another example of, again, a very simple system, except now we have this entry method. So here we have an example program using this slightly different simple char. Unlike before, where the simple char actually computed, it took 2 arguments in the constructor and computed the area right there. Now instead, we create a char, and then 10 times in a row, we call find area. And in this case, find area takes some radius, and then a Boolean flag as to whether the computation is done or not. So we first call it 10 times in a row, saying find the area from 1 to 10, and we're not done. And then we send it another message saying, okay, find the area for a circle of radius 10, and we are done. So the question is, does this program execute as expected? Okay, I see a couple no's.
But your pi set will be done first, as your constructor.
Right, so the pi will be set correctly. However, because of asynchrony, we essentially have 11, well, actually in this case, not a 10, 10 message sends here. And since there's no guarantee in the ordering, these messages could arrive in any order, so there's nothing stopping this sort of terminating message to arrive first, and we only end up getting one area printed out. As far as what you can pass to entry methods, you can pass all the basic C++ primitive types, int, chars, bools, those all work fine. You can also pass at least most C++ STL data structures without any problem. You can pass your native C-style arrays in the following way. So in the CI file, you say, if for this method here, foobar, we want to pass some array of data. We first pass an int saying how much data there is, and then the array of data itself. And then the C file, the actual entry method would look like this. So it has a length, and then it has a pointer to some data. Just so we guarantee that when we're doing the sending, we know how much data to actually send across the wire. We need this extra length parameter. And then when it arrives in our remote char, you also have the length of the data itself.
This is actual code. It's not like we have to put length in the number.
Yeah, that's
a variable.
Yeah, that refers to the variable directly.
Yeah, so you can call this, without any extra recompilation or anything, you can call this method passing an array of size 2 and then an array of size 4 or whatever. So far we've seen examples of just creating one single char object at a time with this ck-new. However, for large computations, especially that want to be very scalable, that run on supercomputers, for example, oftentimes we obviously want, a very large number of chars. So to make this easier, we have groups of chars are what are called char arrays that I'll go over now. So these char objects can be grouped into index collections. Some examples of when you want to do this is a block of a matrix, a chunk of unstructured mesh, portions of a distributed data structure, volume of simulation space, and then a more advanced examples, just abstract portions of computation, interactions among basic objects and real entities. So basically you can declare arrays of chars, so you have large collections, and as we'll look at, they can take a couple different forms. So you can have very structured collections of a 1D, 2D, up to 6D collection of chars. You can also have an unstructured collection of chars where you actually provide the indexing yourself, and as long as that indexing is hashable, you can have a collection of chars defined in that manner. And these collections can also be dense or sparse. So for example, in one of our molecular dynamics mini applications, we have a 6D collection of chars that do computation between pairs of cells. However, not every single entry in the 6D array actually has a char there, because we only are concerned about entries that correspond to pairs in the actual 3D array of cells. And then you can also have the distinction between static and dynamic. So you can create a collection of chars right up front and say this is the size of the array and that's how it's going to stay. Or you can dynamically insert these elements as you need more char objects or delete them when they are done. So here's another example from the tutorial code section. This is an array-based, a char array-based example of a Hello World program. So here we have, again, our main module. In this case, it's called ARR. Again, we have our MainChar main. And then here, instead of declaring a singular char, so before we'd have the keyword char here, now we're saying we want an array of chars. We want a 1D array of chars, and these chars will be called hello chars. We have our constructor that accepts an integer. And then we have our just another entry method on this array called print hello. And this again is in the example under array hello.ci and .c. So here we have the C file. So the main constructor, for the most part, looks the same, except we now in the arguments from the command line we accept some array size. And now when we do the creation, we're no longer creating just a singular char. So when we actually create the object, when we say ck_new, the first argument we have to pass it is how many chars we want in this array. So here we're creating a char array of hello chars, and there's going to be this array size number of elements, and then anything after that is the normal constructor arguments. So to each char in that array, we're also going to pass it the array size. And then here we have a method invocation on a char array. So again, we have a proxy p to this char array, and then we index it. So we want to get the 0th element of this array and actually send the print hello message to that specific char. Now, if we look at the hello char itself, again, it inherits from cbytes hello. It has a field for the array size, which it accepts at construction and sets it there.
That's the second one.
Yes. So you always, when you call ck_new, you tell it the size of each dimension. So for example, if we had a 3D, you have to tell it the size of the x, y, and z dimensions, and then every argument after the first arguments for the dimension size, that's where you actually pass in whatever arguments the char itself needs. So in this case, when we call print hello, it first prints out a message saying hello from, and then whatever char index in the array it is, and also it tells you what PE that char is on. And then if we're the last char on the array, so this is why we passed in the array size, if our index is equal to the array size -1, we'll exit. Otherwise, we're going to send a message to the next char in the array. So again, like each char has this proxy, it also, when we're dealing with char arrays, has a field for its own index. So in this case, we see here that the char is going to get its own proxy, which is the proxy for the entire array. And then it'll get its own index, increment that by 1, and send a message, essentially sending that message to the next element in the array.
Sorry, you may have said I missed it, but in the ck_new, which of those arguments is the array size?
The
Which
first,
is the argument to the constructor?
the first n arguments for an n-dimensional array are going to be the sizes of each dimension, and then everything after that is the arguments of the constructor. So if we look at the tutorial code again, we've already made array hello. So if we do charm run, we'll run it on 4 processors. And again, this expects you to pass in the size of the array. So if we want to do it on an array of size 16, for example, we see that each char reported what PE it happened to be on, and then hello from the first one, second one, all the way down to the 15th one. And notice how here we have this causal ordering, because in the actual way we did the messaging, we first sent to PE0, it did its printing, and then it sends the message to the next char. Right. So you can provide your own mappings, and by default, I think it's a block mapping.
It depends on the array dimension and whether you specify the size up front. Basically, we try to set defaults that would give you same behavior.
Yeah.
Applications that get involved enough nearly all specify a mapping themselves.
But yeah, we just block.
Yeah, divide it up. Yeah.
And again, this is the initial mapping of the chars. If we're doing dynamic load balancing, for example, each element of the array can be migrated if need be to improve load balance, etc.
Okay, so I see the constructor with intent in it.
Yep.
That's the one you actually called.
Right.
What's the other one?
So when we're dealing with migration, here we have an extra constructor that ends up being called during migration. I think we're going to touch on this later during the migration example.
And then this index is an integer.
Yes, in this case.
Oh.
However, again, if you have, for example, more unstructured collections that you want, you can define your indices to be anything that's hashable. For example, in Barnes Hut, I think.
Don't even get there. Even in the 2D case, that's an object that contains an XY pair.
Yeah, so if it was a 2D array, this index.x would give you the x coordinate and this index.y.
And this proxy is a pointer to the entire superstructure. Array.
proxy to the whole collection. Yeah.
So if it's 2D, you'd have this proxy bracket, one bracket.
You'd use parens there. This is,
Yeah,
you can
that's-
use parens for any dimension. We should probably just do that consistently. That's just a limitation of C++ syntax, that we can't pass multiple arguments in the operator or square bracket.
So one thing, again, we're going to touch on this a little bit later, but we have a tool in Charm++ called projections. So if you enable projections for a specific run of your program, Charm++ and the runtime system will collect performance data that you can later look at to see more details on how an application performed. And just to show a sample of projections plot for this particular application, run, like it looks like 12 cores. Here we have a timeline view, and we can see, so the white is idle time, and then this yellow chunk is when it's actually executing a message. So we see in this case, we have on PE0, we ended up with a bunch of small method invocations as we started off in the array, and then once the message got to a certain part of the array that was on a different processor, we have this communication here, and then we pick up here, and it kind of has this stepping down until we end up processing the message at every single char in the array, and then eventually exit. So the projections tool is going to be useful for just looking at different aspects of the performance of a run and kind of trying to figure out where improvements can be made. And projections is something we're going to go over in more detail later.
So you can see that this is how not to write the code.
Yeah. This isn't supposed to be an example of good code. This is obviously bad for parallel performance. So here's just a little bit more detail on arrays. So again, instead of the char keyword, if you're actually declaring an array of chars, you have array, and then the brackets followed by the 1D, 2D, 3D, up to 6D. And then your constructors and entry methods just as if they were any other char you're defining. And in addition, and same with the actual classes or structs you define in the C file, everything pretty much looks the same. Even the name of the class you're inheriting from, you just now have this additional constructor, which for the time being, we're just going to leave empty. We're not looking at migration of chars. We're just looking at collections of chars and how to create and use them.
In the previous example, I was just trying to look, this proxy variable there, that got created by Charm through the compilation?
Yeah, so the C-base hello is going to contain this proxy, and for arrays, it will also contain this index.
Is there a list of all methods that are created in methods and variables?
You're still poking through the header.
So, I mean, the header you can just look at. Yeah.
Yeah,
Some
it's
master.
it's kind of a mixed set of things. Maybe we should have an appendix in the manual that enumerates that kind of thing. We don't currently.
Yeah. I mean, in the majority of cases, this proxy, this index, and cknew will get you through a lot of stuff.
cknew, @sync,
Contribute.
reasons, abort, actually, so that we can print which element. Yeah, there's lots of stuff that could be enumerated, but is mostly not of immediate interest.
Yeah, especially there's usually only 3 things that people care about.
Okay.
It's pretty edge case material.
So as far as here, we go into a little more detail about constructing the char array. So it's constructed similar to a regular char with cknew, except now you just need to pass in also the size of each dimension. So in this case, for foo, we had our 1-dimensional array. We want it to be of size 10. Here we're creating a 2-dimensional array with the first dimension of size 5, second dimension of size 5. And again, you may retain the proxy just as before, so you can message the char. And the proxy does represent the entire array. So to actually message an individual element in that array, you index it with the bracket or parenthesis syntax, and then call the method as you would normally. This index is, again, in a 1D case, it just is an index of the current char array element. In a 2D case, it's an object with an x and a y for the current char array element, and similar for 3D, 4D, etc. So this very, very simple example, when the foo is constructed, it would just print out what index in the array is. So here again is the hello example, which we've already looked that. I don't think this is any different. Okay, so here's how the runtime is actually going to treat these objects. So the system is going to know how to find the objects efficiently based on what collection it's part of and what index it can find its processor. So again, the applications can specify mapping, or if not, the runtime system will try and provide something sane, such as block or round-robin mapping. And the distribution can be static or dynamic. But the key thing about this is the application logic doesn't change at all. Not even depending on what mapping you specify, not in the face of migrations. As long as you have that proxy to that array, you can use that proxy with an index to find any element in the array, regardless of where it is, regardless of whether it's moved. You can call methods without needing to deal with that bookkeeping yourself. That's all handled by the runtime system. So what's nice about that is you can develop and test the logic for the objects without worrying about how they're distributed in the system or where they locate. You have separation of time, division of labor, portability, shared progress. So all these things allow you to really focus on the logic of your application and what it's supposed to be doing, rather than the logic of how do I get these onto the processors, how do I make sure this runs efficiently. That can all be handled by the runtime system, and you can guide that, but again, that can happen completely separately from the actual logic of your application itself. So here is just an example to kind of drive the point home. We have multiple different arrays. We have our C array here, which is two-dimensional. We have an A array here, which is dense. We have A0, A1, and 2. We have a one-dimensional B array that's sparse. We only have elements 0 and 3. The C array is also sparse, it looks like. And so these elements are all going to communicate with each other in some fashion. C elements are going to communicate with A's and B's. And the runtime system can manage how these are going to go on the processors without you having to worry about it. So here we have just an example mapping of the different array elements processors. So notice we can have not only the arrays being mapped separately, but even elements from different arrays on different processors, so we get that very high degree of composability and modularity we talked about before. And then with the message-driven execution, whichever particular array element has method decisions for it, will actually execute on the processor, giving us the overlap of communication and computation. So another very common feature in a lot of parallel applications is collective communication, and this kind of goes naturally with our collections of chars. So our point-to-point operations, which we've talked about so far, are just two objects, the sender and the receiver. However, collective operations, we can have, well, now that we have collections of objects, we can have collective operations on these collections. So the two we'll talk about right now are broadcast and reduction. So if we have a char array and we want to broadcast something to every single element in the array, we can simply call a method that broadcasts to the array. And with the reduction, we would collect a contribution from each element in the object of array to form some final result. And in both cases, a spanning tree is used to send and receive data, so we do that efficiently. So broadcasts in Charm are very simple. So again, we want to send a message to each object in the collection. We already have this char array proxy object, so we can use that for the broadcast as well as our point-to-point sends that we've already seen. And this just looks like any other function call to the proxy object. Just now we don't use an index. So if we have this hello array here, which is an array of hello chars of this size, if we want to broadcast a method to every single char in that array, instead of indexing the proxy, we just call foo on the proxy itself. And this will send a foo message, therefore invoking the foo method on each individual element in the array. And if, for example, you want to, if you are already part of that array and you want to send a message to everyone in the array, you again have this proxy, so this proxy.foo will allow you to broadcast to the array. And from another char, again, that has a proxy p to the char array, again, p.foo will do the broadcast to the whole array. So reduction is kind of the inverse of that. We want to take some sort of set of values from each element in the array and then either sum them, max them, aggregate them, do some sort of operation on them to end up with one single result. So here again, we usually reduce to a set of, or some single value. So the combination of these values requires some sort of operator. Much like MPI, the operator must be associative. It also must be commutative in this case, since we're doing these asynchronous reductions. We don't necessarily know how these operations are going to be applied. and then each object in the array itself, when we want to do a reduction, just calls a special contribute method to contribute whatever data it has to the reduction. So here would be the CI file if we're going to have some sort of reduction going on. In this case, we have some array of elements that are going to do something. At construction time, they get a proxy back to this main proxy, so they all know how to communicate with it. And then now, in addition to its constructor, where we enter the execution of the program, main also has this special reduction target method that will be the target of this reduction. So how this is going to work is every element in the array is going to contribute to the reduction, and once we have the final result, it will show up here in this done entry method, which is the target of the reduction. We'll see how that looks in the C file next.
The bracket reduction target, that's literal. So I just need to substitute.
That's the code.
Yes. Yep. So this is just saying that when we tag a method as a reduction target, in this case, we know there's going to be some sort of reduction that's going to be called, and it's going to end up with an int as the result, and that will end up here.
This is the code.
Yep.
Like standing. No, when there are placeholders in what we show, we're going to be very explicit.
Yes. And also, I forgot to mention, this code is also in the tutorial code. It's called reduction main target, I believe. I'll look at that in a sec. So here we have the C file. So we have some number of elements in our array. Just define that as a constant right now. And then, so what main does is the constructor simply creates an array of these objects by passing it a proxy to itself, so they know where to send the results essentially, and the number of elements in the computation. And then upon creation, each element will use its index as a value in this case, and then what we do is each element we're doing a sum reduction of basically the indexes in the array. So first we create a callback to say where we want the reduction to end up. In this case, our reduction target is going to be called on a main proxy, and it's the done reduction target, which we've defined up there. And the specific proxy that we want it to be called on is our main proxy that got passed in that construction. And then we have our value, and we are contributing. So we call this contribute method or function, which we say how much data we're contributing, what data we're actually contributing, which in this case is just our index. And then we say what kind of reduction it's going to be. In this case, we're summing integers.
What are your choices? You can sum doubles, you can do a max.
Yeah, sum doubles, max. There's a fairly exhaustive list in the manual.
The manual contains the enumeration.
Yeah, it's, I mean, mostly what you expect, min, max, different kinds of sums.
There's logical order. Yeah.
Yeah, concatenation.
There's set union, and there's concatenation of a list.
Can you move reduction function to the MainChar? Sometimes it would make more sense this way. So I don't want my element char to know how to reduce values, but I would like to know. I would like to code this piece in the MainChar. Is that possible?
Well, I guess for example, instead of passing in the main proxy here, the main proxy could have given it a callback saying where we want the reduction to go, and then each char, for example, could say I'm going to contribute my value to some callback that someone told me to contribute to. Is that sort of what you're getting at?
In this case, the scope of the index data is to the element. The MainChar didn't have that data until we contribute the sum back to it.
Oh yeah, so there's a particular point here, which is that reduction is a reduction over the elements of that char array. So it looks for exactly one contribution from every member of the collection. So because main isn't part of a collection, there's nothing to reduce over. So if it has a value, it has one value.
So the reduction function have to be coded inside the collection.
Yeah.
So what's this? How come the constructor arguments don't match with the definition of element?
Meaning the order?
Well, there's this proxy, which is M proxy, and then there's num elements, which just vanish.
Yeah.
So that might be a typo on the slide.
Yeah, that might be a typo on the slide.
The array. Well, right, yeah. So that's a typo on the slide relative to what we described earlier. It works because there's a variant syntax that this leads to. There's an overload for CK new. That it's not actually just the swapped order. That would be very confusing, but there is a different kind of object that can encapsulate size and several other options for array construction that I think is being default. It's being
But we could switch them, and it would be okay.
In this case.
No.
In this case, it's a flip.
In this case,
Yeah.
that
So
works.
the first part is what is going to be in the constructor, and the second last part is XYZ, the number of elements you want.
No,
That's
that,
the order.
Why can't we do it the other way? Because you said you could do
no, it's what's happening is there's an overload for this where instead of passing the size as numerical arguments, you can pass a single object of type CK array options. And CK array options happens to have a constructor from a single integer. So
Yeah, this is just a strange typo that happened to work out.
But if you had written it the other
This
way,
works for 1D arrays.
this works for 1D, but not for anything more.
no, but if you swap the order on the slide,
Yeah.
it would work, and we would not be asking this question.
Yeah.
Yes.
Yes.
So
That's what I wanted to know.
you should imagine it as just
Compiler error.
number of elements this proxy.
Okay, thank you.
It wants the proxy, wants the constructor already first.
Yeah.
Okay, we screwed that up in the earlier slides.
I think it was in the explanation that you gave. Yeah, usually it's the
First
the
part
dimension.
is
The
the-
dimension is the trailing
The
argument.
Yeah.
first part is the constructor argument.
Yeah, sorry about that, you're right. We apparently didn't check all of these carefully as we should have, and confused ourselves.
So we should just reverse everything we heard?
Apparently, yes.
Yes.
Also, MPI is better for writing complicated parallel applications. Reverse everything.
Well, okay,
We
let's
could all be sitting on the ceiling.
So let's look at the actual code to hopefully disambiguate some of this. So again, here we have the CI file for this reduction, which we've looked at before. And then if we look at the CPP file, we have our creation of the array where we say the arguments and then how many elements are in the array. That's the correct ordering. And then in the array itself, here we have we first create a callback to say where the reduction should end up when it's completed. In this case, again, we wanted to call the done method of a MainChar, and then this is the particular MainChar that we want to call that method on. And then we contribute something of size int, which is our index in this case. We want to sum them, and then to the we contribute that specific callback. And then if we now look at what the callback does, in this case, it just takes in some value, which will be the result of the reduction. In this case, we have a simple check to just, because we know if we have elements, 0 through 49, we know what the sum should be. So we're checking to make sure that the value is the correctly reduced value. We print it out, and then we call exit on the program. So if we run this, it's not going to look terribly interesting, but it should run. So again, here we ran it. It's created 49 array elements. Each one contributed to a reduction, its own index, a sum reduction, and then the sum of those happens to be 1,176. So now we've seen broadcast and reduction. Just another quick note about reduction. So just like point-to-point communication, these broadcasts and reductions are going to be completely asynchronous. So for example, when this element calls contribute, it sends off its data to the reduction, and then it can carry on with whatever it's doing. In this case, it's just going to end its constructor, and another element can contribute. But these reductions can happen asynchronously, as well as the broadcasts using the spanning tree.
How many arguments can CKU take? like, so in this case, there was the one num element. Is there 3 or 4 others that it can take that may or may not appear in the constructor? So like it had this proxy num elements, which num elements is, I guess that's interpreted, we were talking about this earlier, and outside of the constructor of the individual element.
So for the most part, you're usually going to see it just taking whatever the constructor arguments are, and then a size for each dimension of the array. So if it's 60 array, you'll have 6 sizes.
Oh, so there'll be 6. Okay.
Yes.
There's the general class of stuff for complicated options.
Yeah.
Which is there's the CK ops object.
Oh, okay.
That you can create that, and you can set a whole bunch of parameters in there,
and then pass that in.
and then pass that as the final argument.
Yes. So you can either pass the sizes explicitly if you just want to say create me an array of this size, or if you want more control, you create this array options object and tell the size and any other information you might need. Pass it.
There's
And
a
then pass
variety of parameters. Things you might set in there would be whether or not, if you wanted the array not to be migratable, for example, that's one of the things you can set in there. You can define what the mapping choice for placement of array objects would be. You can define the object that does the mapping. That would run it using passing ops. There's lots of things about the arrays to get non-default.
Okay, so now we're going to move on a little bit to talk more about the decomposition in Char and how that works. So in this case, we're going to start looking at a divide and conquer paradigm in Char++. So in the divide and conquer, each object is going to recursively create n objects that divide the problem into subproblems. And each object T will wait for all n objects to finish and then combine the responses. So at some point in the recursion, at the bottom of the tree, there's going to be some sequential process that sort of knows to stop there. And then the result is propagated back up the tree recursively.
Sorry, can I ask you something about reduction? What
Sure.
if I want to reduce an array?
So
not just sum the entries, but like get 10 parallel sums.
Oh, yeah.
Yes.
Is it an animal too?
Yes.
You want to flip back to the example code? You can show how to do that.
Oh, the example code.
Well, you got it right here.
Yeah.
So you see this contribute size of int.
Yeah.
So in that case, we're just doing one int, right?
Yeah.
We could change that to 4 times size of int and do it across 4 ints. Then
we just add
and we
an extra
change,
4 ints.
and then the done itself would have to be not the int value, but int star value. Right?
Okay, so it's pretty transparent.
I think it gets harder with multi-dimensional arrays when you want to do across one index of the array.
So some examples of just this divide and conquer that are pretty canonical are Fibonacci or quicksort, and we're actually going to look at a Fibonacci example now. So this is going to be a very naive implementation of Fibonacci just to show a nice recursive structure and how Char++ would deal with it. So in this case, we're going to define these fib objects. Each object will perform one of 2 actions. Either it's going to create 2 new fib objects to solve the subproblems Fibonacci of n-1 and n-2, and then wait for a response. Or if it's either trying to solve fib of 1 or 0, it knows what the answer is right away, so then it just returns it to its parent. So we're going to end up creating this tree of Fibonacci objects, and when we hit the bottom, we're at either n equals 1 or 0, and then that result will get propagated back up to the root. So for example, if we start by wanting to compute fib of 5, that object will spawn one object computing fib of 4 and another object computing fib of 3, and in turn, each of those will spawn 2 children to compute their subproblems, and eventually we get to the bottom of the tree down here, and the result then from each object will be propagated back up to its parents, and eventually fib5 will get the results of fib4 and fib3, add those together, and we have the Fibonacci number, the 5th Fibonacci number.
So in that tree, for example, for fib2 is known privately to fib4.
Yes.
So is there a mechanism to fib4 to create fib2 in a collection that's accessible for others? So fib3 also needs fib2.
Right. So yeah, so this is an extremely just naive example, but for example, if you wanted to do this in an array, for example, you could have chars created at the indices. Like for example, we could have a char created at fib2 that's just in charge of computing the Fibonacci number for 2, and then since fib4 and fib3 are both part of that array, they have, they know the direct address of this fib2. Right.
So, and you can do a sparse array. So.
Right.
Okay.
So sorry, I'm trying to understand this example. I mean, I understand it in the mathematical sense.
Mm-hmm.
So each, like, fib5 is a char.
Yeah, so we're going to actually...
CK news 2 fibs?
Right, so we're going to actually look at this in code, and essentially, just to be very explicit and close to this like mathematical model, we're going to make each fib object here a char. At construction, it's going to receive a number. So for example, this fib would be constructed with number 5. It would call CK new twice to create 2 new chars, each responsible for computing their specific subproblem. And we go down the tree and then
but it would also
walk back
pass
up.
its own proxy to them.
Right, right.
Yeah, you want to just pull up the code rather than...
Isn't that... No, not next.
There's some other things next.
Yeah.
I was wondering about...
Yeah, so if we look at the code then, so... So for example, here we have our CI file, we have our MainChar, and then each fib object takes the number it wants to compute, a Boolean saying whether or not it's the root of the tree, and then proxy to its parent, and then also has this respond method. And then if we look at the C file, so here at construction, if n is less than 2, it's just going to respond with n. Otherwise, it goes ahead and it'll create 2 new proxies, telling them to compute the subproblem n-1 and n-2. Those 2 proxies obviously are not the root of the tree, and it passes its own proxy so they communicate back.
So n less than 2 is n0, fib of 0, fib 1.
Yeah, so if n is less than 2, we know, for example, both 0 and 1 are just going to be the 1. And then, so this is a slightly more, so we're actually going to show 2 versions of Fibonacci to highlight one of the features, but for now, what respond does is it takes whatever value it received from its children, presumably, add it to its result. Then since count starts off as 2, if count ends up at 0, we know we've received both results from our children. And then we decide, okay, if we're the root, we finish the computation. Otherwise, we send our result to our parents and delete ourselves.
You don't need it once you've told your daddy you would.
You don't delete yourself like that.
I wish kids would do that.
No, you can delete yourself as you're executing. That's pretty cool. So the first instance, the parent, it has a very funky way of getting the proxy for itself as it's getting created. Huh?
Yeah, it's just going to get some dummy proxies that we know it's never going to use. Because as long as it's the root, it's not going to try and communicate with a parent that doesn't exist.
So just for the sake of argument, you could cast and put void star. Or
we also probably could have just overloaded the constructor to take 2 arguments in the case where it didn't need a parent, or something like that. Yeah, there's a couple.
Or we could have done the polymorphic thing also, where we pass a proxy that is either fib or main,
and have the result end up back at main. Yeah, there's.
Now, is this a proxy, or is that the specific instance of the object and not a proxy? Down at the bottom.
Oh, this is just like in C++. This is just a direct pointer to yourself.
So okay, so that's me, the
Yes.
real char, as a so can you delete an object through a proxy?
Yes, you can.
Okay.
The method is called CK destroy.
Oh, okay. So if I call this proxy pointer over CK destroy, that's the same equivalent.
Yeah. The reason we couldn't call it delete is because that's a keyword in C++. So we couldn't say, this or proxy whatever dot delete, because the compiler would say delete doesn't go there.
Yeah, it's an operator.
So shouldn't you have the method respond annotated with that special annotation that says it is a reduction method?
So in this case, we're not actually doing any reduction. It's just so when you're done with your computation, you just send a single point-to-point message to your parent saying this is the result I got. And then when you receive a value from a child, you just add it to your current result. So you start off with 0 as your result. You create 2 children. Eventually, the first one will report back saying, I've computed my problem. You add that to your result. If you haven't gotten both responses, you'll just not do anything. And then when the second child eventually responds, you'll accumulate his part of the result and then actually do the, if your root printed out, if not, respond to your own parent.
So what is the respond method actually called after you call CPP or CPKU?
So once we call these, we're actually creating 2 new chars. And again, those chars will start off in their constructor. When they do have a result, for example, if they're at the bottom of the tree, they'll end up calling respond on themselves, which if it's n is less than 2 and they're not the root, then they call respond on their parent. And that will be a message sent to the parent char that created them. So, and again, this is one version of Fibonacci, and then we have a better version later to highlight one of the features we haven't yet got to. But this is how you would do it just with what you have, what knowledge you have right now. So again, with over decomposition, the key is to let the programmer decompose the computation into objects, which we can also refer to as work units, data units, etc. And the key is we want them to define those objects in a way that's natural to the problem, not in a way that is required by the machine. And then the intelligent runtime system, in this case, can actually assign the objects to the processors, can change the assignment during execution if we want to do, for example, dynamic load balancing or fault tolerance. The locality of the data is provides us good performance. Like we said, each object is going to encapsulate its own state, which is generally small, so we're going to have that should all fit in the cache. A parallel object can access only its own data, just like in standard object-oriented programming. As long as you define your actual state as private, it can only be accessed. And so we have the same idea here with our parallel objects. Again, that helps prevent data races and keep this nice, clean encapsulation. We have asynchronous method invocation for accessing other objects' data, and then the RTS can schedule work whose dependencies have been satisfied. Basically, if you have work to do because you have a message waiting for you, you can be executed and do your work. If not, we're not going to sit there and we're going to actually schedule someone else who does have work. So this kind of gets into discussion of grain size and Amdahl's law. So again, remember, if we have k% sequential section, then we can't do any better speedup-wise than 100 over k, essentially. And that's if the rest of the program is completely parallelized. So as a corollary for grain size, if any particular piece of work, or any of our work units, takes greater than k time units, and the sequential program takes some sequential time, then we have this limiting factor or speed up of the sequential time over this grain size. So one thing we've done is we've examined performance data based on varying the grain size to see how the performance varies, and if some are too big or too small, for example, you need to change the decomposition. So
this is actually where Harshitha is.
Okay, cool. And yes, Harshitha will take over and talk about grain size.
Can you re-explain this grain size?
Yeah. So there are some useful graphics that I think will illustrate this quite helpfully in a minute.
It's more or less the following, right? So Amdahl, you know.
Yes.
So imagine you take your work and you divide it up into some arbitrary set of bits. That's what they would call grain size. If one of them is really giant, then that's it. And you should cut it if you want more parallel. So figuring out what the good grain size is. Because usually if you cut the grain size, you need more communication.
Yes, that's
There's
exactly right. Yeah, exactly. I'll talk about that in the next slide. So basically, as you mentioned, so the limiting factor is going to be the char size or the grain size of the largest grain size, because even if you could parallelize all other objects very nicely, this largest object is going to determine how much of a speed up you can get. Like on one processor, it takes 10 seconds. That grain size on 100 processors will still take 10 seconds to execute on one process. And that will be the limiting factor, even if you could nicely parallelize all other things. So there's this misconception that if you keep the over decomposing, if you do too much over decomposition, there is a lot of expense to it. But that's not really true. There is some overhead to it, which we'll talk about. And what do we mean by grain size, basically? So the amount of computation that you do for maybe you're receiving a message, when you receive a message, that is what a grain size is, basically. When you get an event to execute execute some amount of work, that is what is a grain size. So so the idea is we want to, there is an overhead. Let's say messaging takes some overhead. We don't want to make the grain size too small that the overhead is going to be much more than the grain size. That's the key idea. So should the grain size depend on the number of processes? Well, let's look at this particular thing that we are talking about. The grain size is basically the computation per message, let's say. And let's say V is the overhead for the message. And TP is the execution time for when we parallelize this particular work among P processes. And G is the grain size. So the time taken on one processor is going to be whatever sequential time you used to take, plus the overhead, which is V, per message that you get out of the grain size. So you are incurring some amount of overhead too. And when you parallelize it totally, the execution time will depend on either what is your largest grain size, or the T1 by P, which is basically how much of a time did you take, along with the overhead, plus the grain size. So that's what it will depend on. So either the grain size, if the grain size is too huge, then the parallel execution time will depend on the grain size. But if the grain size is too small, then the overhead will determine what is the parallel execution time. That's the idea here. And here is a graph that basically shows how the execution time will depend on grain size. If we have very tiny grain size, then the overhead, let's say it took 1 millisecond for the message overhead, and the grain size is just 10 microsecond or 20 microsecond. So the overhead will determine what is your execution time. But if your grain size is too large, and there are, let's say, P processors, then the maximum grain size will determine what is the execution time. And as we increase the number of processors, so let's say there is one char with 10 seconds, as I mentioned, even if we increase the number of processors, all of the chars could be evenly distributed, which were only 1 second, but there is one processor which gets the 10-second char, and that will determine the execution time. So you will, how much ever you do the parallelization, this 10-second time will be incurred. So the execution time will also depend on the number of processors. So the grain size, the ideal grain size is between this and this point, as you can see. So it should just be more than to amortize the overhead that you get. This is a real run that was done on JYC for Jacobi 3D. So this is a 3D decomposition where the total problem size is 2K cross 2K cross 2K. And as we, number of points per char is the grain size, as we increase the grain size, and the y-axis is the time per step. So for the same problem, as we increase the grain size, how does it affect the time per step? We see that, again, for very tiny grain sizes, there is, the time per step is high, but there is a range in between, this we call a backward curve, where there's a range in between where all the grain sizes kind of give the same time per step. But beyond a larger grain size, that will cause the bottleneck. That will, so basically you're not able to parallelize very well. And other processes are sitting idle when one processor is executing that large grain size chart. So these are other graphs which show the same kind of result. So typically what we have seen using experimentation is about 8 chars or 10 chars per core is sufficient to
get the adequate benefit of over decomposition. That's a typical thing that we try in an application run. But the ideal way to do it is, how much of overhead are we incurring, and what should be the minimum size of the grain size to amortize this overhead. There's another factor to it. Load balancing is also affected by the grain size, right? So if we have a distribution like this, so x-axis is grain size in millisecond, and y-axis the number of objects. So if you have large number, if you have like some distribution like this, where many objects are very tiny size, and there are some objects which are really large size, then it becomes tricky to load balance. Let's say the average load of a processor is only 20 milliseconds after doing this thing. Then we find that there are objects even 40 milliseconds. So we have to put that object in some processor, and that processor will take 40 milliseconds to execute, whereas others will finish in about 20 milliseconds or 30. So the grain size, we should try to shrink the grain size as much as possible, but just enough to amortize the overhead cost. So the solution is to split the objects, computation object, so that they may not have too much work, which makes it difficult for the load balancer to actually balance them out. They should be of tiny size. So we can use many heuristics to decide how do you want to do the decomposition. So here's an example of that. This is molecular dynamics simulation. So basically, the strong scaling is limited by the most overloaded processor, and if the most overloaded processor has the largest char, then it's going to be limited by that. So what do we do to reduce the grain size? So there is one way in which the square patches are the cells, the 3D space is over decomposed into multiple chars. These are called cells, and the diamond ones are the computes. They calculate the pairwise forces between the cells. The cells are decomposed such that they are within the cutoff distance. So if you want to find interaction between two cells, the compute will calculate the interaction between them. This is the 1D decomposition. So we find that in 1D decomposition, that's using the tool called projections. You can get the distribution of grain size and the number of objects using this projection tool. So you can find out how many objects have large grain size and how many have tiny grain size. So this is the distribution of that. We find that, like in the other example we saw, there are many of them most of them with the tiny grain size, but there are indeed some of them with very large grain size. So what do we do in this case? Well, we can do k away, 2 away, 3 away, or k away. So what do? We split the cell into 2. But now to calculate the force interactions with this cell, you will have to talk to not just one neighbor, you'll have to talk to 2 neighbors. So you're decomposing further down, you're making the grain size smaller, but yeah, by incurring some extra messages in this case. So by doing that kind of decomposition, we get a better distribution of this. So now we will be able to better load balance and make sure that none of the grain size is much larger than the average process load. So the rule of thumb is, this is a very common question that we get from people, that what should be the number of chars, how much should we over decompose. So this is the thing that he says, make it as small as you can so that it amortizes the overhead. And so let's say if V is the overhead, we can say, okay, 10 times the overhead. Let's pick a grain size that is 10 times the overhead. And no single grain size should be too large. Let's say on an average, all the processors have 1 second of load. but there is this particular char with 10 seconds of load. And again, the time per step is going to be just 10 seconds. So that's exactly what it said. No single grain size should be too large. And the typical thing we do is, we assign 8 objects or 10 objects per processor, and it shouldn't be much more than 10 times what we talked about the overhead. So you can be as close to the optimal grain size without even thinking about when you go to larger scale what happens.
So just a quick note. Another way to think about this is when you're designing your application and setting up a run, imagine that you have an infinite number of processors, and those processors are still connected by a network with high but finite bandwidth and latency. So you have a fast network, but it's not a magical network. So as long as it's still worth doing a parallel decomposition across more processors with the workload you have, then you should do it. If you had blue team torus stretching out to infinity, but there's still that distance, whatever size problem you're running, you'll want to take, there's some chunk of the machine that's an optimal size. That's how many grain, that's how finely you want to break up individual chars. And then if you happen to run it on a smaller machine, that means the runtime can efficiently tack them to load balance and do communication efficiently and so forth.
And there's work going on to automatically, this Yanma's work on control systems, to automatically figure out what is the right grain size, etc., etc. That will be coming later. So in this Fibonacci example that you guys saw in a few slides back, how do we set a grain size here? So what was happening is each char is spawning new chars, and they are spawning new chars. And you can go on till you reach a very fine grain level, till you have only 2 numbers to find the Fibonacci. That's very tiny fine grain level, right? So the way you would set the fine grain size here is in that example where you had if n less than 2, then respond with whatever number it is. You can decide that maybe after 4 or let's say 10, I'm not going to spawn new tasks because the overhead that I'm going to incur in spawning the new task, I can as well compute it sequentially and do it by myself and respond to my parent. So you stop this tree from propagating until that very tiny fine-grained granularity. You stop the tree from forking new tasks at a certain point. And that you will have to determine what is the right point. You don't want it to be too big and you don't want it to be too small either.
I mean, I understand that if you have a giant grain size, it will limit your computation because it has to go through it.
Yeah.
I understand that there's overhead in sending messages.
Yes.
I understand practically what your guidelines are saying.
Yeah.
Saying compared to the overhead per message.
Yeah.
But how do I know what the overhead?
Well, that's why I said there's this alternative way you can think about it of, imagine you have an infinite number of processors, break it up so that you can make the best use you can of every process. Imagine it's an MPI program with an infinite number of processors.
Okay.
And however you break it up, those processors will still have to communicate. So if you go too small, you have a surface area to volume ratio problem that your communication is going to be your entire data set all the time. So you dial it back just far enough that your communication doesn't overwhelm the computation.
So you know what is alpha beta cost, the message latency, and how much message bandwidth it's going to be to the calculation. And you find that it's X millisecond, let's say. You know what is the speed of the processor. This is way too involved calculation. You know what's the speed of the processor. So you can do so many calculations sequentially on your own thing instead of spawning the new task. That's one way to make it come.
I think the question you have is that new parameter, I think it depends. It depends on the network.
Yeah, no, I mean, I understand the guidance, but it's very hard to know what the overhead per message is, right?
Well, right. So that's why I'm trying to.
empirically.
That's what. Yeah. So ultimately, it'll have to come out of an empirical determination. But that's why, if you think about it, most parallel programmers have a better sense of how much communication is too much, and just think about it in terms of how far can I decompose before communication is overwhelming.
So you guys, the two parameters you typically use are the latency, which means the time of the path on path. Go from a NIC card to inside the process. I can find some latency.
Yep.
And then there's the network speed times the size of your message. So in these analyses, they ignore things like congestion. All other
I get an idea what we're
So just to give you an example, suppose you were writing like a parallel matrix multiply in any parallel thing on a distributed memory computer. You have a huge number of processors and a fixed size matrix. You're still not going to write something where each processor owns a single element of the matrix. You're going to have some block size that each processor, you'll distribute the matrix over, in blocks over that set of processors.
Okay.
Because
that is what you will do, but then you will have to decide on the size of the block.
You'll have to decide on the size
You're
of the
saying
block,
it
and
depends on
ultimately,
the communication.
yeah. So ultimately, yes, the optimal block size is going to be, empirically determined, but it's when you're designing the application, you can tell up front that that block size is not 1. Because you have some intuition of what is or isn't efficient on a parallel computer. And you know that you can't make a matrix block size of 1 and have, one floating point operation alongside sending a message, receiving along a row, sending along column, whatever. So you know that there's going to be a trade-off there. So essentially, as long as you design and implement the application so that that block size is a parameter you can set, when you start up the application, then you can tune that when you do.
Will we have any more code examples?
Yeah, there's code examples kind of all of this.
I'm hoping to see an example which shows a parallel quicksort, for example, or a matrix multiplication. We have something like that.
Yeah.
Because in that case, you have to pass back from your lower char to a MainChar or upper char, not just one single integer, but a piece of an array.
Well, so we
that
actually
would be more interesting.
we showed array argument passing in one of the earlier examples.
The most complicated example we have is like in the tutorial is the 3D Jacobi.
Okay.
Passes around lots of data. A 3D Jacobi.
Yeah, so it's a stencil code. It's a 7-point stencil in 3 dimensions. So you have, a 3D, and then each element is going to pass planes of ghost cells from its boundaries. So it packs those into arrays and transmits those.